Okay, so what we're talking about today is memory. Memory and learning. And memory and learning are obviously things that are involved with one another. Learning is the act of getting the information, acquiring the information. Learning is an act of acquiring information, whereas memory is your ability to go back and get that information you've acquired. So we think about learning and memory in the common world, in the everyday world, in real life, all of the time. We make jokes about it in cartoons. We have common misconceptions. We have common true understandings. And then a lot of stuff is somewhere in the middle. And those are the kinds of things we're going to talk about today. So learning is where you are making a relatively permanent change in your behavior based on experience. Okay, so as a psychologist, if I want to measure your learning, I'm going to see how much your behavior changes. And so that learning can be, you know, a child learning to walk, or it can be a person learning to understand neuroscience, or it can be any of the many things that we can learn and acquire as knowledge. And the important thing is that that changes our behavior. That we are then able to do new things we couldn't do before because of learning. We've acquired new ways of behaving based on experience. And then memory is our ability to go back and get that. Memory is our ability to bring back what we have learned. And we've studied memory in a lot of different ways based on what we might want to know about learning and memory. So one of the first things that you might think of that we would want to know is, how much can humans learn? How much can humans know? And there have been many, many tests on the limits of human memory. Ebbinghaus was one of the first people who talked about learning and memory and forgetting in kind of a systematic way. He tested himself over and over and over. Ebbinghaus was a weirdo. Ebbinghaus kept these very, very detailed logs, huge, thick logs of what he was testing, which was he would make up lists of nonsense words. Okay, so these are words that you can pronounce it, but it doesn't make any sense. Gurg and blurp and all this stuff. So he would make lists of nonsense words, hundreds and thousands of these words, and then he would put them in different orders and try to memorize a list and see how long he could remember it. And he found that as time went on, he could remember them less and less well. And so that became the forgetting curve, the time over which, you know, you start to forget different items in a list you might be trying to remember. And so it got named after him. Now today, if he were to do that experiment, we would say, hey, Ebbinghaus, you have an N of 1. And your number of participants is 1. So we're not going to publish you anywhere. But you know, this was a bygone era. But we went back and tested Ebbinghaus's stuff on other people, and other people performed just like Ebbinghaus, more or less. That forgetting curve, when we've tested on other people, has held true over time. You might want to know you know, how different organisms acquire memory. And so we've done things like we've looked at mice and rats, and we found that depending on what kind of things they're learning, different parts of their brain are active. So like when they're learning a new place, a new space in their cage, for example, like you put a new box on the edge of their cage and they go and they explore it, it activates different cells in their brain. We call them place cells, cells about what place the animal is in. And by this time, you know, we found out all different things about the different areas of the brain and what they contribute to this system of memory that we have. So after we ask ourselves, you know, how much can we learn and what kinds of things can we learn? You know, look at a human being. No matter how much you try, you'll never learn to fly, you know, without some kind of equipment that lets you fly. No, you can't flap your wings enough and learn to do what a bird does to fly. There's limits to what we can do. So how much we can take in and what we can do. And then people wanted to know, you know, are there different places in the brain where memory might be stored? And so what we did is we started lesioning animal brains, okay? And we would see if the deficit the animal ended up with corresponded with what we thought that part of the brain might do. So if we damaged a certain part of the brain and the animal lost its short-term memory, oh, well, maybe that area is involved in short-term memory. And we compared that to people who would have damage to certain areas of their brain. Now, of course, we didn't deliberately do this to people. You know, a person might have a car accident or, you know, a surgery that went wrong or a brain hemorrhage. And so we compare that naturally occurring lesion study to what we might do in animal studies, and we kind of put all the pieces together. So I want to talk a little bit about these different methods first. So we have looked at this point not only these lesioning studies in animals and recording actual electrodes in the animals' brains when they're doing different tasks. We've also looked at MRIs, so static images of brains, and compared different kinds of people who might have superior memory on one thing or another. Does that correspond with a certain increase in size or connectivity in an area of the brain? We can look at that in MRIs. And now we can even use fMRIs to see if the same parts of the brain are activating when the person is learning as when they're remembering. And fMRI data indicates that that's absolutely what's happening. So essentially, when a person is, one of the tasks I can remember watching them test a person on was while she was having surgery, so her skull was open so they could access her brain and put an electrode in. They had her watch a bunch of videos over and over and over again. And then when they asked her, now can you remember what the videos are, the same areas of her brain would light up when she was remembering what she saw as when she actually saw the thing. And so that's a good analogy for what's happening with you. When you are performing a task or bringing to mind something that you've done before, you are activating those same brain areas as when you were learning it. Okay, so now I want to talk about how we categorize memory, different ways of categorizing memory. Short-term memory, long-term memory, explicit memories, implicit memories, all these different kinds of memories, because it's meaningful. It's meaningful to understand, number one, how the human brain does things. So this is how people work. And also that the brain instantiates in a real way these differences. So these differences that we notice behaviorally for hundreds of years end up corresponding with differences in brain processing once we can look at the brain. So I'm going to talk about that right now. Okay. The lowest level of memory you can have, and when I say lowest level, I mean the shortest duration, okay? So this has the shortest duration of memory. And it's probably the thing that you would be least inclined to even think of as memory is called sensory memory. So sensory memory is the actual persistence of the perceived object in your perception even when it's gone. It lingers there for a second or more, even after the stimulus itself is gone. There are two main types of sensory memory, though there's sensory memory for the other senses, it's not as well explored, okay? For vision, the sensory memory is called iconic memory. Iconic memory, like an icon on your computer screen. Iconic memory is this. Have you ever been looking at, like you stare at a light and then you look away from it and it's like you can still see the light when you look over to the dark? Okay, that. Or have you ever had it where it's really dark outside and then the lightning flashes and that just happens for a millisecond, right? And you see like a house and a tree on the hill or whatever you see, and then once the lightning goes away, it's almost like you can still see that image there just for a second. Okay, that's iconic memory, that lightning flash persistence, visual persistence of the object even after it's actually gone. Even after it's gone back to dark, it's almost like you can still see the thing there for just a second. That is iconic memory. So most people probably don't even think of that as memory, okay? It's just persistence in our neurons. For our auditory system, it's called echoic memory because it's like an echo. It's like there's a little loop echo that plays in your brain for a few seconds after somebody stops talking. So it happens constantly. It happens right now in this room. After I stop talking, you guys can actually hear a little bit more of my voice even after I'm done. Okay, so it's like you can still hear me for just a second afterwards. Or like, you know, you hear a song and then you hear that you just hear that echo of the song real fast again for a couple seconds. That's echoic memory. Okay, so it's literally like an echo playing in your head. And that lasts, some studies have found it can last up to as long as 20 seconds, but other studies have said, no, you're really getting into short-term memory there. It's more like it's 4. You're getting into something else when you get up to 20. So there's a little bit of debate, but still we're talking about seconds, not minutes. The next kind of memory is called short-term memory or working memory. And again, this is not something that most people think of as memory. Short-term memory or working memory is essentially how much stuff can you hold in your head at once and work with it. It's the stuff that's in your head right now that's allowing you to interact with the world. So short-term memory is the reason that you can understand an entire sentence. So I say a whole sentence or I say a whole paragraph and you're not confused at the end. It makes sense with what I said at the beginning of the sentence. That's because your short-term memory is holding on to the whole sentence until I get to the end. And then it might let it go. And then the next sentence goes into short-term memory until you get to the end, and then it might let it go. Okay, so short-term memory is what you're dealing with right now in order to be able to, you know, take notes. Remember a phone number to type it into your phone. Remember that the person you just met is named Bob for that conversation and then forget it after that. Okay, so short-term memory, it was called short-term memory for a really long time, and it still is in many books, and you know, professors will call it short-term memory. But people who are in perceptual science, people who work with memory, now they like to call it working memory because it's less about how long it is. Yes, it's true, it's short-term, but it's about what you're working with right now. It's about what's active in your neurons, okay? So your working memory is what's active in your neurons. When you are listening to me right now, if you're paying attention, I'm activating neurons in your brain that are allowing you to understand what I'm saying, to put it all together. That's your working memory, okay? It's what you're working on right now. And that has a limited duration. As you know, you can't keep a million things in your head all at once. You know, the phone numbers that we try to memorize, 7 to 10 numbers is about the maximum we can get people to do, like a phone number. And we have to even get people to know that by chunking it, you know, 760-543-9583 or whatever. I just made that number up. Whatever number you're trying to memorize. Oh my gosh, nobody call that number. I just made that up off the top of my head. Okay, don't call that number. That's no one's number. Okay, all right. Okay, I shouldn't have done it. All right, so, so it does have that limited capacity. And so we use that short term, but working memory is really what we want to go to now. So I'm going to try to call it working memory. Okay, so we got sensory memory, lasts a few seconds. Working memory lasts a few minutes. And then the next kind of memory is usually what you think of when you think of actual memory, which is long-term memory. Memory that lasts days, months, or years. So when you think of memories, okay, think of memories that you have. Does anybody just want to throw out a memory, any memory that you have? Anyone? A memory. Yes.
The birth of my daughter.
The birth of my daughter. I love it. Yes.
Cloudy beach day in Hawaii 2009.
Oh, 2009 cloudy Hawaii beach day. Who could forget that? You guys. Okay, anybody else? Good memory, bad memory, any memory? Okay. Yeah.
First trip to Las Vegas.
First trip to Las Vegas. Ah, yeah. Totally, definitely 21. Okay, so this is exactly what I mean. You guys nailed it, okay? When people think of memories, they think of stuff that happened to them. But that's actually a specific kind of memory. That's a very specific kind of memory called an episodic memory, which is a memory for stuff that happened to you, for biographical events, okay? You experienced it, you went through it, it happened to you, and you have this memory of this day, or this moment, or whatever it is. You also probably think of another kind of memory very closely related to that as memory. So this is semantic memory. So semantic memory is like your memory for facts, okay? So you probably do think of that as memory because, right, when you go to take a test, you have to remember the facts for that test. That's semantic memory, okay? So they're not asking you on the test what you experienced, right? They're asking you to present factual information. That's semantic memory. So, you know, what is a table? A table is a flat object with 4 legs, or however you want to describe it. What is it? It's the semantics of it, the words for it. Okay, so if I say, you know, February is Black History Month, okay? That's a fact. That's a semantic memory. Those two kinds of memory together, okay? Semantic memory plus episodic memory, which are the things that most people think of as memory, and yeah, we get that. I see how that's memory. We call that explicit memory. It's things you can explicitly remember in words. Okay, explicit memory. You can remember this thing in words. You have words that can go with it. Explicit memory. So we also sometimes call it declarative memory for the same reason. These are things that I can declare. I declare that this is how my daughter was born. I declare that, you know, dendrites receive neurotransmitters or whatever. Things that you can declare, things that are explicit, those are all in one category together. Yes?
When it comes to remembering like song lyrics, it's easier when the song's playing in the background. So would that be ecologic, like sensory memory, or would that be long-term memory because you have to hear the song and know what it is?
That's a fantastic observation. So he's asking about music and what kind of memory that is. And the answer is that music triggers all of our different kinds of memory. Pretty much every kind of memory you can think of, from sensory memory through long-term memory, and both explicit and what I'm about to talk about implicit as well as emotional. Music carries all of those kinds of learning in it, and that's why it tends to be learned so well. Because it has so many connections to so many things, it's very strongly anchored in the brain with lots of connections and lots of repeats of the connections. Does this make sense? Okay, and there's whole unbelievable fields of study about that, you know, we could go on about all day. So, but that's a really great observation, and I love that because music really does bring in all of those different things. Okay. So we're talking about long-term memories, and long-term memories in general, they're permanent or near permanent. Okay, they're permanent meaning once you make a long-term memory, it's always there unless something comes in and damages the memory. It is possible to have, you know, what amounts to brain damage that makes it so that you can't retrieve a memory. But pretty much any memory that has ever been, that you've ever made is there. All you have to do is go back and refresh those neurons. So those neurons fired together at one time to make a short-term memory. And then if you did consolidate that memory into a long-term memory, it's there forever. You just need the right context to go back and get it, barring damage. Okay, damage can happen. So the other kind of memory that's under long-term memory is another thing that most people don't think of as memory. And this is your memories for how to do stuff. We call these implicit memories, implicit as opposed to explicit. We also call them procedural memories, meaning it's how to do stuff. So this is a kind of memory. You obviously had to learn to walk when you were a baby. And then you learned it, and now it's in your long-term memory, and you can walk. You had to learn to talk when you were a baby. And you learned to talk, and now you can talk. You had to learn to write. You had to learn to read. You had to learn to, do a layup. Whatever it is that you do with your body, skiing, driving a car, any of those things, you had to learn it. And so now that's a memory, and you do go back and retrieve it every time you use it. But you usually don't think about those things in words. So sometimes some scientists will say these are unconscious memories. And that's not entirely true. What they mean is you can perform these tasks unconsciously. You can, once you've learned to ski, you can just ski without thinking about it. Once you've learned to drive a car, you can just drive that car without thinking about it again. So you can perform these acts unconsciously, but it doesn't mean they have to be. So for example, you are very consciously aware of these things while you're learning them. If you've never learned to knit before, and then you go to learn to knit, it's like, oh my gosh, you have to be very consciously aware of what you're doing, you're gonna mess it up. Or anybody ever try to learn to drive a stick shift? Okay, right? You have to be very consciously aware of what you're doing. Or anything that people may have tried for the first time, skiing, you have to be very consciously aware of where your feet are and this kind of thing. So it's not necessarily that it's unconscious, but it can be performed unconsciously once you've learned it. Does that make sense? Okay, cool. Okay, the last kind of memory that I want to talk about, sometimes they put under implicit, but I don't like to put it under implicit. It's the emotional memory one. Okay, I don't like to put the emotional memory under implicit because it's so different. The reason that we have these categories is not just because behaviorally they're different. It's true that behaviorally explicit learning looks different than implicit learning, but that also looks different than emotional learning. And they use totally different circuits in the brain. Explicit, implicit, and emotional memory are all totally different circuits in the brain. You may be connecting those circuits at the same time based on the same information, but they are different parts of the brain and they're doing different things, and they absolutely can be activated separately. Okay, so that's why I don't like to put that in there with the others. Okay. Let me make sure I've covered everything I want to cover. Okay. Yeah, I'm totally exactly where I need to be. Good. So, emotional memory, I'm just going to mention right now because it's probably the easiest circuit to understand. Emotional memory can occur with an explicit memory. Okay, so for example, if I tell you to think of the person you hate most right now in the world, okay, you are probably going to have an emotional reaction to that at the same time you're explicitly remembering their name, their dumb name. Okay. You can also have it tied to an implicit memory. You know, you remember a time that you fell down and you hurt your knee, and now, you know, you're afraid to walk down that sidewalk because that was where you really scraped your knee real bad, or something like this. So you can have it be implicit, or it can be both. You know, you can look at somebody's face and you can have an emotional reaction and know who they are and exactly what happened, and, you know, they could punch you in the face at the same time. So all these things can be occurring together, but they can also occur independently. You can learn somebody's name and have no emotional connection to it. You can be walking down the sidewalk and have no emotional connection to the behavior you're doing. All those things you could be making, you know, you can learn how to knit and not have an emotion about it, right? It doesn't necessarily evolve an emotion. But when it does evolve an emotion, when you are making memories that have an emotional aspect to them, your amygdala is very active. Your amygdala gets super active when you're making a memory that has an emotional component to it. And especially if those memories are negative. So if it's sad or stressful or angering or any of the negative side of the emotions, your amygdala gets very, very active when you're making those memories. Which is why when you get back into that emotional state, you can start to remember and start perseverating about so many things attached to that situation. You know, you get that anger triggered in you, and now all of a sudden you're back in that same place they cheated on you, and da-da-da-da-da, and all the things you remember, you go right back to that emotional state. And you can remember all of the details that are explicit that go with it, or even implicit that go with it. One hypothesis that is supported by some but not all research is that differences in the amygdala are associated with autism spectrum disorder. So that people who have autism spectrum disorder have a difference in how their amygdala activates from neurotypical people. And we are not sure whether this kind of just happens to the amygdala over time in folks on the spectrum, or if they start out with a difference in the amygdala that causes the behaviors you see that go on from there. So let me explain. Autism spectrum disorder is thought to be a primary deficit with understanding certain social cues, and specifically a lot to do with face and vocal information. And so it could be a number of different things. For example, it could be that folks with ASD are sensitive to that kind of information, to facial information and auditory information. And so they kind of push it away because it's too overwhelming. So they start out, it could be that they start out with an a very sensitive system that then leads them to not want to engage with faces and voices, and so they don't learn about faces and voices the way a neurotypical person does. Or it could be that the person is processing all of these things all along, and it's just that whatever that difference is in the brain makes it so that you're always processing faces different than other people are. And so you don't become an expert in faces and voices the way a neurotypical person becomes an expert in those things. You become an expert in something else, whatever else it is you wanted to pay attention to, whether it was your drawing or your cars or whatever it was that your deal was. And one's not good and one's not bad, it's just different ways of dealing with information. So that's one of the hypotheses about what's going on with folks with ASD, but we're not sure. It seems that the amygdala is probably involved, but exactly how, we're still figuring that out. Okay, So now I want to talk about the neural circuits that underlie the other kinds of memory, okay? So there are actual circuits in your brain that are responsible for you learning different kinds of memory. And I hope it makes sense when you put it into the perspective of things you already know. Okay, has anybody already watched that last Little Vision lecture? The one that was just like 20 minutes long? Okay, a few people. In that, and you gotta, okay, promise, there's an essay question about it. Okay, in that little video, I talked about the dorsal stream versus the ventral stream and what those two things do. And that the dorsal stream that goes from your occipital lobe, where your primary vision is, up to your parietal lobe, where you do somatosensory processing, that's your how pathway. How do I interact with the world? And the one that goes ventrally from your occipital lobe with visual information to your temporal lobe, where you have language information, that's your ventral pathway, that's your what pathway. Now hopefully you can see how those things are related to your different kinds of memory. When you learn explicit memory, when you learn explicit memories, what you are trying to do is make connections primarily in your temporal lobe. Explicit memories are explicit memories because they're explicit memories because you can put words to them. And what lobe is responsible for language? Temporal lobe. Okay, temporal lobe is responsible for housing language. So when you are learning new explicit information, new language-based information, like I was here and they were there and we did this, and the temporal lobes do this and the occipital lobes do that, all of this is stuff you can put into words, and we are putting into words. That's explicit information, and what we want to do is make connections in the temporal lobe. So when you are learning explicit information, like you are right now, learning explicit information if you're paying attention, your temporal lobes are very active. That's your working memory. As you're listening to me and you're dealing with this information right now, your neurons in your temporal lobe are activating, and that's your working memory. But what we want to do is make it so that when you take the test, you can reactivate those same neurons. We want you to be able to reactivate those same neurons at the test so that you can give the right answer. And in order to get the information from short-term memory to long-term memory, you have to do a process called consolidation. In order to get information from short-term working memory, where it's just current activity of your neurons, into long-term memory, you have to do something called consolidation. And what consolidation does is it strengthens the connections between the neurons. It changes, it restructures the connections between the neurons in a permanent way. That's what memory is. Not temporarily activating your neurons, but by activating your neurons, we make permanent or nearly permanent, barring damage, the connection between those neurons. That is the process of consolidation. And for explicit information, the part of your brain that you need to consolidate explicit information is called the hippocampus. It's right up here in green, hippocampus, kind of a teal green, outside the amygdala, right next to the amygdala. You can see it right here, this blue spot right here, and then this is it right here. The hippocampus is part of the medial temporal lobes. That's the medial, the inside part of the temporal lobes. The hippocampus is right there. The hippocampus is one of the main structures of the medial temporal lobes. Some other structures in the medial temporal lobes that are very important are entorhinal cortex, and parahippocampal cortex. What does that mean? If this is the hippocampus, parahippocampal means the little bits of cortex right around the hippocampus. So hippocampus and right next to the hippocampus, that's parahippocampal. And entorhinal means behind your nose, inside the nose, towards the nose. And that's because, guess where this stuff is? Right behind your nose. It's right in there, okay, if you were to be able to get your... Here's your temporal lobes. If you were to drill into them to get to the medial part, you'd be right behind your nose. So entorhinal cortex, parahippocampal cortex, hippocampus, these parts make up the medial temporal lobes. And those are the parts that consolidate explicit short-term memory into explicit long-term memory. So if you think about it, it makes sense. Your temporal lobes are where your neurons are activating, and if I want to solidify that activation to make new connections between neurons, I just use the little guy who's right underneath the temporal lobes, the hippocampus. The hippocampus is chilling there right underneath the temporal lobes, right in the medial part of them, and it's the guy who's kind of like, I like to think of it as a signal booster. He's the guy who becomes very active when it's time to learn something and remember something. Okay, so when you're really focusing on something, when you're concentrating and you're learning, or even if you're just repeating it over and over and over and over again, your hippocampus is solidifying the connections between the neurons in your temporal lobe. The more you do it, the better your memory gets. The more elaborately you make the connections, the better your memory will be. So this is ventral route stuff. Implicit memory, you shouldn't be surprised to learn, is going to involve motor stuff and body stuff. So the pathway that goes dorsally from your visual cortex in your occipital lobe up to your parietal lobe, which is your somatosensory processing, your stuff about where am I in space? What am I touching? Where's my hand? What's this? Oh no, it's squishy, okay? That part of your brain that processes that somatosensory information is your parietal lobe. And so when you are learning implicit memories, when you're learning how to walk as a baby, when you're learning how to ski, whenever that is, when you're learning how to drive a stick shift, when you're learning how to knit, when you're learning how to do any new activity, any new procedure, it's that pathway, the dorsal pathway, that's highly active. And while you're doing it, your neurons are activating. And the part of the brain that helps you consolidate that, the part of the brain that helps you consolidate implicit information, is right underneath the parietal lobes. And it's called the basal ganglia. You'll remember the nigrostriatal pathway went from the substantia nigra to the basal ganglia. That's an important pathway for motor learning. It's your motor learning pathway. Your basal ganglia is the signal booster for learning implicit memories in the same way that your hippocampus is the signal booster for explicit memories. So basal ganglia is what does the consolidation for how to do stuff. And that makes sense because it chills right underneath the parietal lobe, which is where you need to be making the connections. So you have the current activity here in the parietal lobe and the basal ganglia right underneath saying, hey, make those connections permanent so that we can keep knowing how to walk or keep knowing how to drive. Explicit memory gets a lot of feedback from other parts of the brain. So this is in your book, and I put a copy of this page in my notes so that you can just print it out and bring it and understand what it says, and you don't have to draw it yourself, okay? So I'm trying to save you some time from having to draw this from the books. The top depicts the circuitry for explicit memories, then implicit, then emotional. Explicit memories, the important thing to understand is that there's a lot of feedback. When you're making explicit memories, the other parts of your brain are monitoring it for essentially truthiness. Does this fit in with everything else I know? And if something seems wrong, your brain will put a brake on it and inhibit that learning. It will say, wait a second, that doesn't fit in with what I already know, and inhibit the learning. So your brain is constantly monitoring for errors. And that's good because you usually do catch yourself when you make a mistake. Oops, I forgot this, or, you know, whoops, I wrote that letter weird, or whatever you're doing, you catch yourself and do it again. So when you are doing explicit processes, you get a lot of feedback from the rest of the brain. Whereas with implicit learning, it's mostly one way. You just start doing the action, and then you just keep practicing the action over and over and over again until you get it fluid. So imagine, you know, practicing learning to walk, and then you're practicing the baby first things you learn in tennis, and then you learn the next class worth of tennis, and then you keep learning, and you get better at each step until all of those steps become automatic, and then you're Serena Williams, right? Whatever you practice is what you become. Whatever you practice is what you become. Whatever you practice is what you become. Alzheimer's disease and Parkinson's disease have distinct symptoms because they attack distinctly different systems in memory. So most people are familiar with Alzheimer's disease. And the progression of Alzheimer's disease, which starts where the first thing you have trouble is remembering new memories, like where you put your keys that morning, or, you know, what you had for breakfast. And then as time goes by and the disease gets worse, you start forgetting what you did the day before, and the day before that, and the day before that, etc. It deteriorates the newest stuff first and the oldest stuff last. And Alzheimer's, the first place it attacks in the human brain is the hippocampus. The hippocampus is, if you'll see an Alzheimer's patient after they've passed, their hippocampus will be shrunken. So what does that mean? It means they have trouble consolidating new memories. If your hippocampus doesn't work, new things that you learn won't stick. You can't learn new explicit memories. And then the disease attacks the cortex, and it starts killing the neurons. We can try to let the neurons that you do have function the best we can by using acetylcholinesterase inhibitors, as we've discussed before, but eventually we don't have any way to stop Alzheimer's as of right now in a permanent way. It is going to start to deteriorate the rest of the brain. And the thing that deteriorates first are explicit memories, because it is attacking those parts of the hippocampus and the cortex. But the last things that will be deteriorated with Alzheimer's, number one, is implicit memory. Alzheimer's patients can be very strong and have very good coordination of their bodies even till late, which can sometimes be trouble when they don't know where they are or what's happening, but their body is still very strong. Presents its own whole set of problems. But also the memories that are the most connected. Whatever pathways in your brain are the most connected are going to be the ones you lose last. I keep saying whatever you practice most in your life is what you become. I tell this story of my mom. My mom was the smartest person I've ever met, and she died over a period of 6 months. She went from being brilliant mind, like, 160 plus IQ, to dying in the course of 6 months, and what she had was anoxia. She had periods of time where oxygen didn't get to her brain because her lungs were failing. She had leukemia. And those periods of time that cut off oxygen from her brain, parts of her brain died. And I watched her go from this brilliant person who had this incredibly complex mind, I watched her lose the different parts of her mind. I watched her lose herself, her consciousness. And over those 6 months, by the time it got to the last few days of her life, the last week, she was not talking. She was just basically a skeleton, she was fixing to die. And I went to see her every day, and the last thing I said to her before I left that day was, "I love you, Mom." And she whispered back to me, "I love you." And that's because that was the most practiced thing in her entire life. It was the very last thing she lost, but she never did lose it. So if love is the thing you practice most in your life, it'll be the last thing you lose too. Parkinson's disease attacks the opposite part of memory. Parkinson's disease attacks that pathway from the substantia nigra to the basal ganglia. It attacks a motor pathway. And so you see the motor problems that you do in Parkinson's disease. People have trouble initiating movement, and because the basal ganglia is not getting its input, they have trouble learning new movements. And again, Parkinson's disease is a disease that will eventually deteriorate the entire brain, but you're going to be keeping your explicit memories for a lot longer with Parkinson's disease because that's not the system it's attacking first. So these are degenerative to the point where they eventually will, take over the whole brain and lead to death. But, you have long periods of time, sometimes years, like look at Michael J. Fox, where the explicit part of his brain is functioning just fine, but the motor part of his brain, the part that's responsible for movements, is what's having trouble. And who was the guy who first showed us all of this? Who was the guy who we credit with understanding all of this? The guy who we credit with understanding all of this is a guy who, when I took this class in 2007, he was still alive. He passed in 2008. So when I took this class in 2007, we still called him HM. To protect his privacy, he was only known by his initials. But he had already had, hundreds of articles published about him. Well, since he passed in 2008 and they revealed his name, it's Henry Molaison. And Henry Molaison is a very interesting cat, and he's the guy who taught us about all of this stuff. So Henry Molaison had severe seizures, and he was living in the 1950s. He had very bad epilepsy. And eventually the epilepsy became so severe that he was having many seizures throughout the day, and he couldn't have any kind of normal life. And so he went to a surgeon, named Scoville, and Scoville recommended what he thought was the cutting edge procedure at the time. No pun intended, cutting edge, right? He recommended, he said, the origin, we can put all these electrodes on your head and we can tell that the origin of your seizures is in your medial temporal lobes. Okay, does this sound familiar? So we're going to cut out a little piece of your medial temporal lobes on both sides, and hopefully that will stop the seizures. And it did. It did stop the seizures. But it came with a cost, which is that he lost his ability to consolidate explicit memories. If you don't have your hippocampus and parahippocampal cortex and entorhinal cortex, if you don't have those parts, you cannot consolidate new explicit memories. So, has anybody ever seen the movie 50 First Dates with Drew Barrymore and, how she loses her memory every day? That movie is extremely loosely based on the case of HM. So what HM had was everything else worked perfectly except for the consolidation of new explicit memories. So what does that mean? His working memory was fine. He was actually very intelligent. You could introduce yourself to him. He would talk to you and have a lovely conversation with you and remember you. But then as soon as you left the room, you ceased to exist. He couldn't consolidate that new information. However, his implicit memory was completely intact, so he could learn to do new things. He could learn to do things like play a video game. And he would have no idea even what a video game was, but he would be getting better and better and better at it every day. And so every day he would see it. Oh, what's this new machine? I've never seen this before. Oh my gosh, I'm awesome at this. Okay, so his implicit memory was great. His retroactive memory was great, both for implicit and explicit. He could, of course, remember all the things he learned to do with his body, walk, talk. He could do all that stuff. But he could also remember stuff that happened to him before the surgery. He could remember his childhood and, you know, jobs that he'd done and his parents and all that stuff. So he had memories. He just couldn't make new explicit memories. Does this make sense? Okay, so we're going to watch a video about HM now. Hopefully. Okay, it's the very last thing, and it's literally repeating what I just said, so I'm going to send you a link to the video. I don't want to waste your time trying to find the link to the video. Okay, so does anybody have any questions about this stuff? Yes.
It's not necessarily about it, but I have read things on how being put to sleep, like with, but being put to sleep can also influence Parkinson's.
Being, like having anesthesia?
Yeah.
Can cause Parkinson's?
Yes.
Oh, I haven't heard. I would have to see. If there's some new link, send it to me.
Okay.
Send it to me.
All right.
Okay. All right, so you need to watch the video, okay? It's just like 10 minutes long, but I'll send you the link.